Hello friends, so today we are going to solve 5 questions, and these 5 questions are from electrostatic, and mainly we are going to deal with the electrostatic potential energy along with the other concepts also. So the first question states that find a geometrical arrangement of one proton, 2 electrons such that potential energy of the system is exactly 0. How many such arrangements are there with the 3 particles on the same straight line? So we are given that we have 1 proton and 2 electrons, and they are to be arranged such that the total potential energy of the entire system is equal to 0. And they are to be arranged in the straight line. So we are given that we are having a proton. So we can write that as a plus E, and we are having 2 electrons, and we can write them as minus E and minus E. And we know the standard formula for the electrostatic potential energy. You can say that electrostatic potential energy of a system of point charges we already know their general formula. So we can say that is equal to U, and U will be equal to 1 upon 4 pi epsilon naught summation, and this is our Q of I, Q of J, and the distance between our I and J. Okay, so this is the basic formula for electrostatic potential energy for the system of point charges, and we are going to use this formula. And in the question it is mentioned that the potential energy or electrostatic potential energy of the system should be equal to 0. So let's find out the condition for 0 potential energy. Condition for 0 potential energy, and let us denote. We are having our 1 proton, so we are going to denote this proton as our P, and we are having 2 electrons, so we are going to denote them E1 and E2. Okay, this is the only notation. Later on we can just put there plus E and minus E if required. Okay, otherwise we will keep them like that only. So we can say that our total potential energy will be equal to, this will be our E square divided by 4 pi epsilon naught, and we have our minus 1 upon distance between a proton, 1 electron, minus 1 upon distance between proton, second electron, plus 1 upon distance between first electron and second electron. Okay, this is the general formula. We have not fixed the position of our proton and electron. Okay, so this is a simple general formula, and we want that this should be equal to 0, and therefore we can write that 1 upon R E1 E2 should be equal to 1 upon R proton electron, first one, and this is our same for now for our second electron. And this relationship defines the geometrical arrangement, all geometrical arrangement for zero total potential energy. So we can say this relation defines all geometrical arrangements for zero potential energy. Okay. So if you want that our potential energy should be, total potential energy should be zero, then this relation will be always true. Okay. Now we are given that all these charges are linear. Okay, they are in straight line. So we can say that we are having a linear arrangement and so in the linear arrangement we can arrange one proton, two electron in two different ways. So let us write case 1. And case 1 is when we are having a proton in between the electrons. So this is first electron, this is second electron, and in between we are having a proton. Okay. And suppose the distance between electron and proton, first one is our A, the second one is our B. Therefore the total distance between these two electrons becomes A plus B. And as per this relationship, okay, so we can write that our R distance between electron 1 and electron 2 will be equal to A plus B, and distance between one proton and first electron is our A, and the distance between the proton and the second electron is our B. Therefore we are going to substitute them and we get this as 1 upon A plus B is equal to 1 upon A plus 1 upon B, or we can write in this as our A plus B divided by A times B. Okay. And the further solution we can write this as our AB is equal to A plus B and its whole square. Okay. And if we try to solve this particular equation, this will be a quadratic equation and this will be having no positive real solutions. So we can say that our AB and A plus B whole square, this has no positive real solution. If there is no positive real solution, it means this arrangement of case 1 is not possible. Okay, possibility with respect to that our total potential energy should be equal to 0. Okay. So from here we can just draw this conclusion. Okay. So we can summarize it that no zero energy arrangement, no zero potential energy arrangement. Now we come to our case 2. And in case 2, we are going to say that we are going to swap the position of our proton and electron. So this we assume is our proton, and here is our first electron, and this is our second electron. Similarly, we can say that A is the distance between our this one, B is our electron, and this becomes A plus B, the total distance. And therefore, from here we can write that our distance between our proton and first electron is our A, and distance between our proton and second electron is our A plus B, and distance between two electrons is our B. So once again, the standard relationship which we have derived, okay, we are going to make use of this equation, and this gives us that 1 upon B will be equal to 1 upon A and 1 upon A plus B. And we can write this as our, we can take our LCM, okay, and this will be our A times A plus B plus, and this, no sorry, not plus but equal to, this will be equal to our B, and this comes as 2A plus B, and we can solve it further. So this will be giving us A square minus AB minus B square is equal to 0. And let us divide this equation throughout by B square. So we get this as A square upon B square minus A upon B minus 1 is equal to 0. And let us assume that A upon B is equal to our x. Therefore, we get this as our x square minus x minus 1 is equal to 0. So this is a quadratic equation, and we are going to get this as a solution of this will be 1 plus square root of 5 upon 2. Okay. So it means it has a, you can say, okay, and if you substitute value of A and B, so we get A upon B is equal to 1 plus square root of 5 upon 2. So this in general is going to give us a relationship between A and B. So we are going to get 2A is equal to B 1 plus square root of 5. Okay. If you require, you can just solve it further, but that is not required because we got one solution for the quadratic equation. It means that the geometrical condition for our equation that is having potential energy is equal to 0 is possible if the relationship between A and B is this one. Okay. And if we look closely, this relationship, or we can say ratio of A upon B, this is nothing but a golden ratio, 1 plus square root of 5 upon 2. This is in general is also called as a golden ratio. And there is only one possible arrangement. Okay, so part second was how many arrangements. So we can say from here only one possible arrangement will be there for the potential energy equal to 0. Okay. Next question. And this question is also with respect to the potential energy, but here the arrangement is a little bit typical. Only arrangement is typical, rest of things follow quite easily. It states that 3 protons and 3 electrons are to be placed at the vertices of a regular octahedron of edge length A. how many arrangements are there and what is the energy of each. So we are given that we are having a regular octahedron, and the vertices, the edge length is given as A, and we are supposed to arrange 3 protons and 3 electrons. Okay, how many arrangements should be there and what will be the potential energy in each case? Okay, so this is the basic question, and in general we are going to use our potential energy general formula. Okay, so we know that the potential energy, in the first question we also wrote it, is equal to 1 upon 4 pi epsilon naught summation for charge qi, charge qj, and the distance between the two. Okay, so this is our energy for a arrangement general formula. Okay. And we are given that we are having a regular heptagon, octagon. Okay, so we can just draw an approximate figure, and so let us suppose this is the one of the vertex and the second one, and the third one, and we are going to get this as and then we can, let us suppose another one is here, and okay, so let us join these first, this, and then we are going to draw the back one. So this will be our back one somewhere here, and we can just join them. So this is our regular octahedron, and let us call these vertices as our V1, V2, V3, V4, and the front one is our V5 and the back one is our V6. Okay, so these are our 6 vertices, and edge length is given as A. So this is edge length, and the opposite vertices will be at a length of, so this V1 and V3 will be our opposite vertices, and this opposite vertices is going to have a length of square root of 2 and A. So we are given that we are given a edge length. Okay. So you can say we are having a edge length, that edge length is A, and we can also write that opposite vertices and these opposite vertices are going to have square root of 2 times A. Okay. And second, we have to and so we are having the opposite vertices. Okay. So therefore we can further state that each vertex is going to have the 4 nearest neighbors. Okay. We can say that our each vertex it is going to have 4 nearest neighbors at distance A. and we are going to have one opposite vertex at distance square root of time a. Therefore, we can write that total number of pairs and this can be over 62 and that will equal to over 15, and these 15 we can divide them into 12 edge pairs. So 15 we can divide this 12 edge pairs and 3 opposite vertex pair. Opposite vertex pairs. And faces we do not require in this question. Total 8 faces will be there, and there will be total over, we can say, 4 opposite pair faces will be there, but that is not required. Okay. And each edge pair is going to have a distance of a, and 3 opposite vertex pair is going to have a distance of over square root of 2 times a. And please remember, we are going to arrange this 3 protons and 3 electrons. Okay. So let us figure we already have drawn. So let us mark our 3 opposite pairs. So we are having opposite pairs, and from the figure we can clearly see that opposite pairs will be our V1, V3, V2, V4, and then we have V5, V6. So these are the 3 opposite pairs. And because we are going to make some arrangement, so let us assume that our these pairs V1, V3 and V5 are having positive charge, and V2, V4 and V6 are having negative charge. So the protons are placed at V1, V3 and V4, and our electrons, these are placed at V2, V4 and V5. And these opposite charge have, you can say, they are having the same length. Okay, that is our square root of 3, square root of 2 times a. And we can also make the, you can say, okay, let's find out their energy first. Okay, and then we have, or let's make the edge pair also. Okay, that will be much more easier, and therefore we can write based on this our edge pairs. And edge pairs, we are going to start with V1. So we V1 with our V2, V1 with our V4, and V1 with our V5, and V1 with our V6. Okay, and this we are going to repeat. So we have already done our V1. Now we do our V3. So V3 with our V2 and V3 with our V4. One second. Oh, my mistake. This is V1, V3 and V5, and this is V2, V4 and V6. And so we got this as V3, V4, and then we have V3 with our V5, and then our V3 with our V6. Then we come to a V5, and this gives us that with V2 and V5, and what else is left? V2, V5 is left, and we have our V2, V3 is left, and we are left with our V4, V5, and we are left with, I think one pair is missing. 1, 2, 3, 4. These two is 12, so one is missing. V1, V2, V1, V4, V1, V5, V3, V2, V3, 6, 2, 5, 2, 3, and 4, 5. Okay, I think V4 and V5 should be missing. Okay, we can check later on also, it's not a big problem. Therefore, we can say that these are having 12 and the distance between them is our A. Okay. And in this case, these like our V1, V3, they are having same charge. V2, V4 is also having same charge, and our V5 and V6 are having opposite charge. Okay. Let me check. Yeah. So therefore, we can say that our, if we look closely, this V1 and V2, they are having opposite charge. V1 and V4 are having opposite charge. Okay. And V1 and V5 are having same charge. And our V1 and V6 are having our opposite charge. So this we have to take care. Okay. And so this was our arrangement number 1. Okay. And V1, V3, V5, V2, V4 and V6. Okay. And V1, one second. So we have our V1, V3, they are having same charge. V2, V4 are having same charge, and yeah, that's good now. And let us come to our second arrangement. And here, let's assume that our positive charge we are placing at our V1, V2 and V5, and negative charge we are placing at V3, V4 and our V6. And here let's find out what will be our opposite pairs. And so opposite pair will be our V1, V3 and V2, V4, and we are going to have V5, V6, and all these are having, you can say, opposite charges. So this will be also attractive, this will be also attractive, and this will be also attractive. So in this case, all we are having the attractive forces. And now let's find out our edge. And edge, we can say that is our V1, V2, and we have our V1, V4, then we have our V1, V2, V1, V4, and V1, Y5, and we have V1, V6, and V1, V2 are having same charges, so this will be repulsive. V1, V4 are having opposite charges, so this will be attractive. Similarly, this will be repulsive and this will be attractive. Okay. Therefore, from this we can say we are having 2 repulsions and 2 attractions. Now we come to our second one, and second one we can write this as our V3, V2, V3, V4, V3, V5, and we have having our V3, V6, and V3, V2 is going to have our attractive, V3, V4 will be repulsive. Similarly, this will be attractive and this will be repulsive. So once again, in this case, we are having 2 attractive and 2 repulsive. And now we come to the last part, and last is our V2, V5 and V2, V6, V4, V5, and we are having this as V4, V6. So V2, V5 will be our attractive, so this will be repulsive, and this will be attractive, and this will be repulsive. So therefore we can say we are having 2 attractive and 2 repulsive. Therefore, for our edge, we can write that total there are, you can say, 6 attractive forces and 6 repulsive forces. Therefore, we can say that total we are having 6 attractive and 6 repulsive forces. Okay, so we have identified the forces. So most of the work is done. Now we come to our solution part. Okay. And in the arrangement 1, so this was our arrangement 1. I forgot to mention here. So this was our arrangement 1. And this arrangement 1, you can see that all these 12 edge layers are having opposite charges, okay, and these opposite pairs are having same charges, okay, like V1, V3, they are having same charge, V1, V5 are having same charge. Similarly, all the opposite charges, these are having same charges, and if they are same charges, we are always going to get our repulsion. Okay. and all these edge pairs are having opposite charges, and therefore we can say all this is going to give us our attractive forces. So we are able to identify that our these two arrangements are possible, and we are able to identify when there will be attractive forces and when there will be repulsive forces. And okay, so let us solve now arrangement 1. The only typical part is identification of the arrangement of these charges. Rest is quite easy because we can just use our standard formula. For this arrangement 1, we know that we are having 3 opposite pairs, and these 3 opposite pairs are having like charges. And whenever there are like charges, obviously there will be repulsion. Therefore, we can say that for this energy for these opposite charges will be equal to 3 times 1 upon 4 pi epsilon naught, and this will be plus e square upon, and the distance between these two are square root of 2 times a. Okay, because we have already defined that there are 3 opposite vertex pair. Okay. So these 3 opposite vertex pair, like is our V1, V3 is quite visible to us, and the distance between these opposite vertex pair are this square root of 2 multiplied by a. Okay. So there are a total 3 opposite vertex pair, and there are 12 edge pairs. Okay. So in the first case, we assumed that our opposite vertex pair are having opposite charges. Okay. Like this is our V1 and V3, they are having same charges. Okay. And so the major differentiation is that in the first case, we assumed that the opposite vertex pairs are having same charges. Like V1 and V3 are opposite vertex pairs. V1 and V3, they are having same charge. And similarly, second one is our V3 and V4. Okay. Sorry, not V3 and V4, but our this V2 and V4, okay, and likewise. Okay. And in the second case, in arrangement 2, we assumed that all these charges, that V1, V2 and V5, they are having the same charges, and V3, V4 and V6 are having also the same charge but negative. So this is the major difference between the two. Okay. So based on this, we made all these arrangements, and the basic figure which we have considered is this one. Okay, we have marked the vertex V1, V2, V3, V4, V5 and V6, and based on this we know that there will be total 12 edge pairs rather, and there will be 3 opposite vertex pair. Okay, so you have to remember this thing. Now we can easily use our basic formula for our potential energy. So in arrangement 1, there were 3 opposite pairs and they were like charges. Okay, so we can say our U opposite will be equal to 3 and its value. And then we are having this 12 edge and all these were opposite charges. And therefore we can write that U edge will be equal to 12 times 1 upon 4 pi epsilon naught, and this will be minus E square upon A. So therefore we can find out that total potential energy in the first arrangement total potential energy in first arrangement, let us suppose I have a U1, will be equal to the summation of these two, and we get this over E square upon 4 pi epsilon naught times A, and this comes as minus 12 plus 3 by square root of 2. So this is the total potential energy in our first arrangement. Now we come to our arrangement 2, and in arrangement 2 we are having 12 edges, and these 12 edges, 6 are having like charges and 6 are having unlike charges. So we have our 12 edges, and 12 edges we know that 6 is our attraction, and attraction means opposite charges, and we having 6 repulsion. Repulsion means like charges. It means the potential energy of this our opposite charges is minus 6 times A, okay, and A will be, because the 12 edges is going to have a distance of A, so distance, everything will be same, and for this like charges this will be coming as plus 6 times A. Okay, A is any, so we can write this as our plus 6 and minus 6, and if we add them, okay, so we can say that our U edge will be equal to, this will be coming as 6, and this is a plus E square upon A, and this will be plus 6, and we have minus E square upon A, okay, and these two terms cancels out, this comes as 0. Okay. And then we are having this opposite vertex contribution, so we can say we are having 3 pairs opposite vertex, and they are, you can say, repulsive. Therefore we can say that our U opposite will be equal to 3 times 1 upon 4 pi epsilon naught, and this comes as our minus E square root of 2 times A. And total energy in the second case, that is U2, will be equal to, and this will be minus 3 times E square divided by 4 pi epsilon times A, and this comes as our, one thing is missing, square root of 2. So these two are the respective energies for our two different arrangements. Okay. And if we make a comparison between our arrangement 1 and arrangement 2, okay, arrangement 1 is more having a strong bond, because it is having a higher negative energy, okay, and as compared to this second arrangement, this is the minor difference between the two. Okay. So in this particular case, the only typical thing is to identify the pairs. Okay, rest is very easy. So first of all, we need to draw a regular octahedron, identify the these vertices, and we should be knowing that from the vertex we can, from the diagram we can say there are 12 edge pairs, and the distance length of the edge is given as A, and there will be 3 opposite vertex pairs, and each is having a length of, the distance between them is square root of 2 times A. Okay. And the vertex pair are our V1, V3, V2, V4 and V5, V6. Okay. And then we define how the charges are distributed. Okay. So we fix the position of the charges with respect to these vertices. Okay. And then we can move around rest of the charges. So if we are able to fix the charges, draw the diagram. Rest is basic, you can say a simple formula for energy calculation, which is quite easy. Next question. It states that calculate the potential energy per ion for an infinite 1D ionic crystal with a separation A, that is a row of equally spaced charges of magnitude E and alternate sign. So we are given that we are having a one-dimensional ionic crystal with the point charges of magnitude E, and they are placed alternately from minus infinity to plus infinity. So this is the basic question. So we can say that we are given that we are having a point charge, and that point charge is given as E, and it is also mentioned that the separation between each is given as A. Okay. Therefore we can just write that they are placed at, and that will be x is equal to 0 plus minus A plus minus 2A plus minus 3A and so on. And we have to remember with alternate sign. With alternate sign. So one second, we have to find out the potential energy per ion. Okay. So for the sake of convenience, let us assume that we take a reference ion and place it at origin. Okay. So you can say potential at a reference ion. Potential at a reference ion, and we assume that this reference ion is our positive ion, so that will be plus E and placed at origin. Therefore we can say that at a distance on either side of this our reference ion, we can find out what will be the charge. So you can say that at a distance Na, because there are n number of charges on either side, the charge is, and we can write it general formula, Q of n will be equal to minus 1 raised to power n times E, and the value of n is going to vary from 1, 2, 3 and so on. And because it is given that it is having an alternate sign, okay, so charges are alternate, plus minus plus minus plus minus so on. Therefore we can write that our electric potential at origin due to all other ions, you can say our electric potential at origin due to all other ions, and that is suppose over V, then V will be equal to 1 upon 4 pi epsilon naught summation n 1 to infinity, and this will be true for our positive side as well as negative side. So this will be minus 1 n times E n A plus minus 1 raised to power n, and this is times A, because this is symmetric left and right with respect to origin. Therefore we can generalize this formula and you can write this will be over 2, and this comes as 2 times E and 4 pi epsilon naught A, and this is summation n 1 to infinity, and this is minus 1 raised to power n divided by n. So this is a general potential for our origin because of all other series. And we are going to use a, you can say, for the solution of this we are going to use the power series expansion of our logarithmic series. So for that we are going to use that natural log of 1 plus x is equal to our x minus x square upon 2 plus x cube divided by 3 and so on. And let us put our x is equal to 1. Therefore we get this is natural log of 2 will be equal to 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 and so on. Therefore we can write that summation our n 1 to infinity minus 1 raised to power n divided by n is nothing but our minus natural log of 2. Therefore we get that our potential is equal to minus 2 e natural log of 2 divided by 4 pi epsilon naught times A. Okay, so this is the potential. Now we are interested in finding out energy, and energy is nothing but our charge multiplied by the potential, and we remember we have to find out energy per ion. So we can say our energy per ion, and that is our U, and it will be equal to Q times V. Okay, but we know that with respect to our origin, which is our at each position left and right are symmetric. Okay, so every is going to, so like this is our minus of E and this is also minus of E, then at origin there will be 2 contribution because of this. Therefore we are going to write it per ion will be our half. Okay, so this factor 1/2 is because of the double counting pair interaction. So this is important here. So we can say that this factor half avoids double counting interaction. So our this Q is our plus E. Therefore we can say that our U is equal to 1 by 2 E, and this is minus 2E natural log of 2 divided by 4 pi epsilon naught times A. And here this 2 and 2 cancels out. Therefore we get that the energy is our minus E square natural log of 2 divided by 4 pi epsilon naught times A. Okay. And so this value is same for, or we can say negative ions by symmetry, okay, because it is entirely symmetric. Next question. And in this case it states that an infinite chessboard with squares of side S has a charge plus E at the center of every white square and a charge of minus E at the center of every black square. The work W required to transport one charge from its position on the board to an infinite distance from the board. Given that W is finite, do you think it is positive or negative? Part B, calculate an approximate value of W by removing the charge from the central square of a 7 by 7 board. So we are given that we are given infinite chessboard, and then we are going to solve it for our the 7 by 7 board. But for infinite, we are supposed to find out whether the work done will be positive or negative. So with respect to our electrostatic potential energy, we can say that if there is charge Q and there is external potential V, then the electrostatic potential energy will be equal to Q times V. Okay, and from there we can easily find out the work done part. So we can say that the electrostatic potential energy of a charge Q in an external potential V, it is given as U is equal to Q times V. Therefore, from here we can write that work required to remove the charge to infinity, and suppose that work done is a W, then that that work done will be equal to difference in their potential energy, electrostatic potential energy. We can say potential energy at infinity minus potential energy on the board. And we know that our potential energy at infinity is 0. Therefore, we can say that work done is equal to minus of U, and this is our board energy, or we can say minus of U, and we can write this as the interaction energy also. And so we can say that if U is less than 0, we get that W is greater than 0. And in this condition, we have to do work. Okay? We must do work. And in the second case, if U is greater than 0, this gives us that W is less than 0. Therefore, we can say the system does the work, or we can say system expels the charge. Expels the charge. Now we come to part B. We are given a 7 by 7 square chessboard. So So we are given 7 by 7 board, and we can just draw 7 by 7 board. So this is our 1, 2, 3, 4, 5, 6 and 7. This is 1, 2, 3, 4, 5, 6 and this is 7. So this is 7 by 7, and from the center of this we have to remove the charge. Okay, so this will be our center part. From there we are going to remove the charge. So left and right, it is symmetric with respect to the center. So we assume that our the removed charge is our plus E, and it is at the center, and this center we assume this is our origin now. So we say that let the removed charge is plus E be at the origin. Okay. Therefore, from here we can generalize the formula for the placement of all the squares. Therefore, we can say that center of all other squares, and their coordinate we can write this as our x comma y, and this x comma y will be equal to m times s and n times s, where this m and n belongs to z, but under the condition that this m and n cannot have a value 0, 0. Okay, this is our center for all other squares. And so we can also say that our charge at any square m comma n, we can write this our charge mn will be equal to -1 raised power m plus 1 times E, because the charges are positive and negative placed on the black squares as well as the white squares. Okay, because the nearest neighbor are going to have the because this is black white black like chessboard. Okay, so the nearest neighbor is going to have the our opposite sign. And we can also write the distance from the origin. Say that our distance from origin, and let us call this as Rmn, will be equal to our s times m square plus n square. So this will be for any location mn. These two relationship will be true. Now we are supposed to find out our electrostatic potential energy, and let us find out what will be the electrostatic potential energy formula according to these two general formulas. Therefore, you can say that our the electrostatic potential energy of the central charge with respect to rest of the board. And we have assumed that the origin is this one, okay, and because we have solved, and this is having a plus E charge, okay, at rest of the board we already know is having a charge of QMN at any general location Mn. So based on this we can write that U will be equal to summation 1 upon 4 pi epsilon naught, and this will be a first charge and any charge at the location Mn and the distance between the origin and the charge Mn. But we have to remember that our M, N cannot be equal to 0, 0. This because the test charge is already at the origin and each square is holding only one single charge. Yes, we have to remember this. So now we substitute value of QMN and RMN. So we get this as our 1 upon 4 pi epsilon naught, and QMN is our E and E, so this comes, we can take it out squared, so this will be E square and summation, so we get this as our minus 1 M plus N and M square plus N square, okay, and there will be S, and this condition will be true here also. Our this is M, N cannot be equal to 0, 0. Okay, so we have to remember this condition with respect to our summation. Now we come to our 7 by 7 board. So value of M and N are our 7 and 7. Okay, therefore we can write this generalized formula for our 7 by 7 board. Okay. So we can say for 7 by 7 board, and we can write the value of our M and N. So we know that our value of M, N, it is obviously going to lie between plus 3 and it is going to lie between our plus 3 and minus 3. Okay, both positive and negative we are considered symmetric, but under the condition that our this M and N cannot be equal to 0 and 0. So it means there will be total 48 charges surrounding the central one. Therefore from here we can say that there are 48 charges surrounding the central one. And for symmetric, because this is a symmetric board, so we can say they are all at the same distance and contribute equally. So therefore we can group them. Okay. Symmetricity has the advantage that if the distance, because the charges are same, although they are opposite in charges, they are alternate, plus electron, minus, positive, negative, positive, negative, positive, negative, but the important part is that they are symmetric, okay, because it is a 7 by 7 board, okay, like this. We have already drawn this basic one. Okay. So wherever we go, we are going to get a symmetric. Okay. Because of this symmetricity, we can just group them. So you can say that by symmetry we can group them with respect to our distances, and therefore we can find out their sign. And for that, let us group them by distance. By symmetry, group by distance. And so let us consider, and we have to remember that this we have taken as origin. So it will be something like this, and this is our origin. So left side positive, left side negative, and right side positive, upward positive, and same. Okay. So this is our origin. So this is going to have our positive, negative, positive, and negative. So let us first of all find out the representative, how our m and n will be distributed. So this will be our m comma n, and then we are going to find out our distance, and then we are going to find the multiplicity, and finally we are going to find out the sign, and that is going to give us a final contribution. This table is going to help us to solve it quite easily, and we are going to consider also the shell. Okay. So let us consider our first shell. Okay. And we are having this is plus minus 0, and this is our 0 plus minus 1. Distance is our 1 unit from the center, and there are total 4. Sign will be negative, and contribution is our minus 4. Then we come to our second. So we are going to have this as our, let me write it clearly. So this will be plus minus 1, and comma 0, and this is our 0 comma plus minus 1. And next we come to this is our plus minus 1, and this is our plus minus 1. So distance will be our square root of 2, because distance we have already formula written here. Where it went? This is the formula, and here s will be common. Okay, so we can just place s here. Okay, distance is our r, and this is s. So s will be present in every equation. So there is no need to further solve it. And so multiplicity will be 4, and sign will be positive. So this will be giving us plus 4 divided by square root of 2. And similarly, we can just draw our third one. So this will be coming as plus minus 2, and comma 0, and this will be 0 comma plus minus of 2. Distance will be 2, contribution 4, and the sign will be positive. So this will be 4 by 2. Okay. So likewise, we can find out all the contribution. Okay, and we have to remember that the value is going to vary from this. And likewise, we can formulate the table, and finally we are going to get this as our 9, and this will be our plus minus 3 and plus minus 3. and this will be square root of 18, this will be 4, sign will be our positive, and this will be becoming plus 4 divided by square root of 18. Now we can just add all these values, contributions. Therefore we can say that the sum S will be equal to, this will be plus minus 4 by root 2 plus 2 minus 8 by root 5, this will be plus 4 square root of 8 minus 4 by 3 plus 8 square root of 10 minus 8 square root of 13, and finally plus 4 square root of 18. And this will be approximately equal to minus 1.416. Okay, so we got the summation, and now we can say that energy of our 7 by 7 will be equal to minus 1.416 E square 4 pi epsilon naught times S. So it was you can say lengthy calculation, otherwise this is quite easy. And then we come to next question. So in this case it states that 4 charges plus q minus q plus q minus q are located equally spaced interval on the x-axis. Their x values are minus 3a, minus a, and plus 3a respectively. Does there exist a point on y-axis for which the electric field is 0? If so, find the y value. And we have to consider this question very carefully, because whenever we you can say consider these type of questions, we simply focus on the sign, and it looks like the sign exists in pair, and therefore there should not be any value of y. But if you solve it diligently, we can clearly see that there exists a value of y. Okay? And so first of all, we are given that when x is equal to minus 3a, we are having a charge of plus q, and when x is equal to over minus a, it is having a charge of minus q, and when x is our plus a, it is charge of plus q, and when x is equal to over plus 3a, it is having a charge of minus q. And we have to find out a point on y-axis. For that, where the electric field is equal to 0. Okay. So we are having this as our plus a plus 3a minus a minus 3a, and the charges are our plus q minus q plus q and minus q. And let us consider that there is a point P. And point P is at a distance of y from this origin. So for charge, any charge on x-axis, so we can just generalize this entire equation. So we can say let the point is P, and this P is at 0, y. Therefore, we can say the distance from charge at x naught 0 to P, and this x naught is vary according to these charges. Therefore, we can say that distance r will be equal to our x naught square plus y square and its square root. Okay. And let's find out what is the electric field of a single charge at any position x of I. We generalize formula and then we can solve it in detail. So you can say that electric field due to charge q of I at x of I and 0. And let us suppose that electric field is our E of I, and we can write this as our K Q of I, and the distance x of I, x unit vector, plus our y unit vector, and distance we can write this as xi square plus y square, and this comes as our 3/2. So this for any charge q of I, and that charge q of I is placed at y. So from x of I we can find out its electric field, and we can find from here we can divide this into two components, x component and y component. Therefore we can say that its x component will be equal to minus k q of I, and this is our x of I, xi square plus y square 3/2, and we are having the y component will be our k q of I y upon xi square plus y square, and this is our 3/2. Okay. And let us find out what will be the summation of all the charges vertically. Okay, vertical component rather. Okay, because we are having a vertical component and we have horizontal component, and we are having these 4 charges. Okay. So based on this we can divide this formula according to the placement of the charges. So we can say sum of vertical components, that is our E of I, and we have the charges are arranged symmetrically. So we can say we are having an inner pair, and inner pair is our plus minus A, and we are given that our minus Q, it is as a minus of A, and our plus Q is at plus of A, and the distance is our same. So we can say that our R is equal to our A square plus y square. Therefore we can say that electric field in y direction because of the inner pair will be equal to k, and this comes as y, and distance is the same 3/2, and this is our minus q plus q, and this comes as equal to 0. Now we come to our, this was our inner pair, and then we come to our outer pair, and outer pair we are given that our plus q is at minus 3a, and we have having minus q, it is at plus 3a, and our r is equal to 9a square plus y square and its square root. Therefore we can write electric field in vertical direction because of the outer will be equal to over k y upon 9a square plus y square 3/2, this is our minus of q plus of q is equal to 0. So it means that the total vertical field, that our vertical field at position 0 comma y is equal to 0, and this will be true for all values of y. So it means basically vertical balance, and that was true also. Okay. Now we come to our sum of our horizontal components. Sum of horizontal component E of x. Once again, we take our inner charge. Inner charge is at our plus minus a, and therefore we can say that at minus a we are having a charge of minus q. Therefore we can say that our horizontal component at minus a position, because of minus a position charge, will be equal to minus of k minus of q, and this comes as our minus of a square plus y square, and this comes as our 3 by 2, and this comes as our x minus of a will be equal to, this will be our minus kq upon a, and this is our a square plus y square 3 by 2. Now we come to at plus a, charge is plus q. Therefore we can say that our horizontal, because of charge at plus a, we are going to get this as minus of kq, and this is our a upon a square plus y square 3 by 2. Okay. Now we can find out their total x because of our inner charges, which is equal to, because these are same and sign is also negative, so this comes as minus 2kq upon a, and this is our a square plus y square 3 by 2, and direction we have to remember is our leftward. And now we come to our outer charges. Outer charges we are having plus minus 3a, and first is our at minus 3a, charge is plus q. You can say that electric field horizontal, because of charge at minus 3a, this will be coming as plus kq 3a divided by 9a square plus y square and 3 by 2. And at plus 3a, charge is minus q, so we get electric field horizontal because of charge plus 3a will be equal to minus kq divided by 3a, and this comes as 9a square plus y square and 3 by 2. Now we can find out our total electric field because of our outer charges will be equal to plus 2kq divided by 3a 9a square plus y square 3 by 2, and it will be rightward. Okay. And it says that our x component should be equal to 0, total x. Therefore, we can say that our total x component should be equal to 0. So, which means that x component because of the inner plus x component because of the outer, this is our x because of the outer will be equal to 0. And so we can simply substitute them. We get this as minus 2kq, and this is a upon a square plus y square 3 by 2 plus 2kq 3a divided by 9a square plus y square 3 by 2 is equal to 0. And this 2kq, a and a we can just cancel out, and this gives us, now it's only calculation part, so this is about 3 upon 9a square plus y square 3 by 2 is equal to 1 upon a square plus y square 3 by 2. And this will take a little bit of tricky part to solve it, but you can just try to sort it out. So this comes as 9a square plus y square is equal to, this will 3 and 2 by 3 a square plus y square, and we are going to arrange it with respect to y. So we can say that our y square is equal to a square, and this comes as our 3 2 by 3 minus 9 1 minus 3 2 by 3, and therefore from here we can say that y is approximately equal to 2.53 times a. So there exists a point on y where the electric field will be equal to 0. Okay. And this is a little bit tricky. If you look at the question, intuitively it looks for us that electric field, there will be no such point, okay, but there will be a point for which our electric field is equal to 0, okay, because x component easily balances out each other, okay, because everything is, sorry, not x but vertical component, that is quite true also, okay, because we see this y component is equal to 0, but our x component of electric field, because of the various distance how they are arranged, okay, and because of this their summation is not equal to 0, and their summation is not equal to 0, we are able to find out the value of y such that the total electric field is equal to 0. And we can say that the vertical component cancel out pairwise because of the opposite charge at equal distances, and the horizontal component is having a inner charge and there is an outer charge, and the distance between them is different. Because of that, we are able to find out a value on y where the total electric field is equal to 0, because the vertical electric field is 0 for entire value of all the values of y, whereas this horizontal component will be 0 when our value of y is equal to approximately 2.53 times a. So this question was, last one was a little bit tricky, okay, and other one which we did was of octahedron. Okay, here we have to find out what will be the value of our this energy, and for that we should be knowing how the charges are being placed. Okay, so that is a important part here. So I know that this, you can say, dates are almost out. Okay, and so hopefully everybody of you will do well in the respective examinations. My best wishes are with you. Still you got the time, so just continue grinding on. That's only option left. Thank you.